don't have much time at all. Okay. So where I have my mark is that we're at the top of page 585, just about to start talking about the Bezier curves. Now, I think I mentioned them before. Did I go into them at all? 585. It seems like I mentioned them, but I don't think I went into much detail. The Bezier curves were invented in the 1960s, so they're fairly recent. That probably seems old to you, but I remember the 60s, okay. By the French engineer Pierre Bezier, who lived 1910 to 1999, worked for the Renault car company. And anyway, I won't go into more. Well, I will say this. They're based on the properties of Bernstein polynomials introduced 50 years earlier by the Russian mathematician Sergei Bernstein to study approximation of continuous functions by polynomials. And today, Bezier curves are used in graphics a lot. Illustrator, Corel Draw, all those things use a true type, PostScript fonts, various things like that. So either of those would be potential paper topics. Bezier, Bernstein, his polynomials, these polynomials, how they're applied, lots of different paper topics you could get out of them. All right, now, trying to see where this, oh, there it is, okay. So parametric curves, I'll blow this up to begin with. Man, I thought this was for later, but all right. Okay. Parametric curves are widely used in the field of computer graphics. A particularly important class of curves are called the Bezier curves, which we discussed here briefly in the cubic case. Now, the cubic case means you go up to the third degree polynomial, the cubes. But they're 4-parameter systems, okay? Now, just to give you an idea of what's going on here, and this is rough, but hopefully you'll see. X of t, now this is a parametric equation, A0 1 minus t cubed. Do you know where the 3 comes from? Okay. Are you taking like the... Okay. Have you heard of the binomial expansion? Okay, Pascal's triangle. Okay. It's when you are expanding a binomial, that's what it's called, binomial expansion, okay, raising it by various powers, these coefficients show up every time, okay? And that's why I asked about Pascal's triangle, because that's a very easy way to come with it. The way I first learned, before I learned about the Pascal's triangle, the exponent here times not this coefficient, but the 1 that's there, okay? Exponent times coefficient divided by the number of terms. This is the first term, 3 times 1, 3 divided by 3, that gives you this one. You drop 1 power here, okay? Now you get 2 times 3, 6 divided by 2, 3 again. Okay? Drop a power here, 1 times 3, 3 divided by 3, third term, you get a 1 there. Okay? Now, notice what else is happening here. This is starting out with t to the 0th power, t to the 1st power, t to the 2nd power, t to the 3rd. Whereas, on the other hand, the 1 minus t starting off with the third power, second, first, the zeroth power. So you got one variable going up and one going down, except they're dealing with the same variable. It's just now. Have you been exposed to any probability, things like that? Yeah, probably not too much. In statistics and probability, the probability that something's going to happen is 1, okay? If there's no way around it, the probability it's going to happen is 1. Now, the probability that it might happen in this certain condition, then you might say is P, okay? So the probability it's not going to happen is 1 minus P, right? Because the total probability is 1. So this, to me, looks like a probability issue that you've got T or 1 minus T. It is or it isn't, type thing. I don't know if that's where this is coming from. I haven't studied any of Bézier theory or Bernstein theory or any of the others, but that's what it smacks of to me. But then you got one thing decreasing power, one increasing. But those were the coefficients. Now, since I mentioned it, I'll go on and give you the easier way to do that than what I just described. Blaise Pascal, I guess, was the one who came up with this. Now, this is going to shrink this when I do it, but this is Pascal's triangle. Okay, remember we're dealing with binomials usually, and let's just say, all right, here's the silver. Doubled the class size in one fell swoop. Okay, good deal. Now, let me get my pen set up. This is not calculus we're doing now, but it's things that you run into in calculus a fair amount. Let's say the polynomial 1 minus t, since we got it there, okay? 1 minus t to the 0th power, what would be the coefficient? That's 1, good. And 1 minus t to the 1st power, of course, what coefficients have you got there? 1, 1, right? And then 1 minus t to the 2nd power, what would be those polynomials? Haven't you done those before? 1, 2, 1. If you expanded that, those would be your coefficients, right? Okay. And we see this is it for the 3rd. 1 minus t. I really should probably be putting plus in there just to keep it from doing, because it doesn't have to be minus, but since we use minus. This one just came up being 1, 3, 3, 1, right? You want to hazard a guess of what the coefficients for that one would be? I'll do the outside. Okay, I know that relieved your mind a lot, for me to do the hard ones there. Any guess? 4, 6, 4. Now, let's go back and do it the way we did before. Starting off with something to the 4th power, 1, something to the 4th power. 4 times 1 is 4. Yeah, that's going to be a 4. Got it? Then 4 times, it would be 3. You drop 1 power. 3 times 4 is 12, divided by 2 is 6. Drop a power, that will now be the 2nd power. 2 times 6 is 12, divided by 3 is 4. And yeah, it's working out that way. Do you see the pattern? Okay. In Pascal's triangle, 1, 5, 10, 10, 5, 1. Do you see how I got that? Okay. Add the two numbers. Notice how you put them between. And these two you get these two you get those two you get these. One's on the outside. 1, 6, 15, 26, 15, 6, 1. Yeah, and you can expand that forever. And every one of those stands for those polynomials. Thank you, Pascal. Okay. Thanks, Blaise. I needed that. I didn't want to have to do that calculation every time. This is Pascal's triangle. Used largely in probability. Pascal was quite a gambler, I think, so he liked to figure a lot. I think he and Descartes, I think it was. I don't remember which one. There were at least two of them that just really loved to use their mathematical genius to cheat. Yeah, I mean to beat other people and things. And they developed statistics and probability and statistics just by their love of gambling. So later it was actually Florence Nightingale that actually came up with some practical uses for statistics rather than gambling. Okay, and she did on health care, you know, and things like this. So she was actually one of the first applied statisticians who actually used it for good. In my mind, good. Okay. Of course, they thought it was good if they were winning money. But anyway, that's, since I mentioned it, these to me look like Pascal's coefficients. Okay? Binomial coefficients, they're actually called. Okay. So there was our x of t, was that expansion. And then the y of t, almost identical. Okay? The y of t, the only difference I see here is that the t's and y minus t's are exactly the same. It's just your coefficients are now different. For x, it was b0, b1, b2. I mean, a0, a1, a2, and a3. Now it's b0, b1, b2, and b3. Okay? So those are your four parameter systems of a cubic polynomial. The reason one more parameter than the power, you have a zero power for this one here and a zero power for the 1 minus t there. Zero power for t here and zero power for 1 minus t here. So you actually have, that gives you your four terms. So these look like they're pretty related, okay? The variables are expanded exactly the same. The only thing that differs is the coefficient. Okay. Now, the Bézier curve where C of t is equal, that's your curve, made up of these two, the previous and this one, are each of your coordinates. Okay. The Bézier curve, oh wait, sorry. No. All right. Did leave off something here. Where they got the points. Sorry, the slide didn't mention this, and I just blew right past it. You've got 4 points, okay? 4 control points. And the x's and y's came from this, okay? The first control point, the B0 point, is the point A0, B0. So those coefficients weren't chosen at random. They came from the points. The x coordinate of one point, the y coordinate of another. P1 would be A1, B1. P2, the second point, is A2, B2. And the third one, P3, was actually, it's the fourth point, A3, B3. Okay, so that's where the coefficients came from. They were actually the corresponding coordinates of the 4 points that you're dealing with. Okay, now, and that's where you get these two parametric equations. Now, I hope they have the next figure. Yes, they do. Thank you very much. I was going to hate if I had to draw them. Okay. So this is how the cubic Bézier curve landed in the place for these 4 points. Now, here's your P0, P1, P2, and P3, 4 points. And this is the coefficient for that first term of your Bézier parametric equation for x, and there's the next coefficient, the next one, and then for y, those are your coefficients. So if you do that expansion, then you see that the first and the last, they land exactly on, and this gives the curve, a cubic curve that comes closest to fitting the other 2 points. Okay? Now, frankly, that doesn't look like it comes all that close, but it seems like you could do a little better than that. And then if you, let's see, no, it's more than just changing the order. This is different, but this time it's doing P0, P1, P2, and P3. Okay, this is the shape you're trying to get with the curve here. Now you have the Z shape, okay, Z-ish shape, and if you're fitting those, then it dips down to go to this and dips up to get to that. So again, the first and the last points hit right on the nose, and you give the best cubic curve that you can fit in between those. Those are the cubic Bezier curves specified for those 4 control points. Notice the zigzag gave you the wavy line, the polygonal shape just gave you a curve. Okay. Now, so what? I mean, how do you use these? When you're trying to do computer graphing and you're moving from one thing to another, you don't want sharp breaks. The curves actually make it look almost more natural and real. Okay. But again, if you're interested in it, sounds like a great paper topic to me. Okay. Now, example 10 is going to use this concept. Show that the Bezier curve is tangent to the segment P0, P1 at P0. Okay? I guess we're going to stay with the cubic. Pretend there's 4 points. We only know 2 of them. Okay? Okay. There was some verbiage before example 10 that I wondered if I should do, but both of you have your books, right? Yeah. Okay. That paragraph in the middle there, does your book have the Bezier curve? Okay. That paragraph is talking about what it's trying to do is keeping the tangent right. And like I said before, it seems like there would be a better cubic to come closer to that, but the other thing it's trying to do is keep the tangent. So you have another constraint here. The tangent has to be the same as the tangent for the blue line, that's same for the pink curve. So that's the other thing that's coming into play here. Because if you had allowed this to go up and rise a little bit outside that line, you probably could have gotten the curve, but it's also keeping the tangents equal. Notice here, between P1 and P2, the tangent on the pink curve is the same as that line that connects, and the tangent between these 2. So that's the other thing that it's doing, controlling for the tangents coming in. So that keeps it from being able to meet them. Sure, there could have been a better cubic fit, I think, to those 3, but not with the tangent being held to what it had to be. So not only does it have to hit at P0 and P3, the tangents have to be right at P0 and P3, and then you fit the cubic curve the best you can. Okay. So the Bezier curve through point P0 at t equals 0, we must show that the slope of the tangent line at t equals 0 is equal to the slope of P0, P1. Okay? So, notice here we're not dealing with any numbers at all except t equals 0, and that's it. That's all. Okay? So let me see. I think what I'll do is write on this curve because it's dealing with it. I think the next curve is another slide altogether. Okay. So let's write these down. X of t is equal to the A0 t cubed, right? No, 1 minus t, I'm sorry. 1 minus t cubed, I forgot which way we were starting from. Okay. And frankly, I don't think it matters which one you start with, but they start with it this way. 1 minus t cubed plus 3a1 t times 1 minus t squared plus 3a2 t squared 1 minus t plus a3 t cubed. Got it right? Yeah. Your y of t, very much like that, except rather than having the a's, you use the b's. b0 times 1 minus t cubed plus 3b1 t 1 minus t squared plus 3b 2t squared 1 minus t plus b3t cubed. All right. Now, the first hand, okay, we are requiring that the slope of the tangent line to the curve be equal to the slope between P0 and P1. So we first need to identify that. M sub 0. I'll count that the slope at your 0 point. Okay, that's equal to B1 minus B0 over A1 minus A0, right? All right. Here is faith. All right, just missing Marcus. He was here this morning. I hope he'll come back, make it in. So this is what we're wanting to show, is that the slope at this point, the P0, is that for your Bezier curves as well. How would you go about getting slope from curves? Okay, let me go back a slide or two, or three. There we go. The dy dx, that's going to be your slope, is dy dt over dx dt, or y prime of t over x prime of t. Okay? Remember that? Theorem 2. Okay. So what we need to get for our, I'm just going to call it dy dx, which we hope is going to turn out being the same thing. Let's figure out what that was. Well, that's your y prime, let me write it this way, dy dt over dx dt. Okay? So first thing we need to do is do dy dt. Can you help me out on that one? Let's call it y prime of t. A little louder? Yeah, well, yeah. Now, however you do that, it's up to you. But let's do the first term. What would that be? Say again? Yeah, let's do the derivative of that one. Yeah. What would that be? Okay, now what you could do, you could expand that 1 minus t cubed and do it that way. Let's not. Let's do it maybe a little simpler than that. How would you do it?
So B is a variable.
No, b is a constant. Yeah, t is the variable. That's why it's dy dt. Perfect. Well, yes, perfect attendance. Way to go. All right, after breakfast, after lunch, perfect attendance. Boy, my second class though today was not. Hopefully my fourth one will be, but we'll see. Way to go. Okay, yeah, y is your dependent variable, t is the independent variable. So you're doing dy dt. B is, all your b's are constants. Of course, 1s and 3s are constants, yeah. So, what would that be? 3 b0, good start. 1 minus t squared. And what? All you need is, yeah, a minus sign. Chain rule, remember? Okay, so it's just like a power. It is a power. 3 times this thing to the second power times the derivative of this thing. That's the chain rule part. The derivative of this is minus 1. Okay? Everybody see it? That's the first term. Let's move to term 2. Okay? This is going to take a bit of thing. I'm going to go on and put a minus there because I know that it's going to come out a minus. So what do you get? 6b1. Okay, now we have a product rule coming into play. Either that or you would have to expand the 1 minus t squared. So let's try to do a product rule. Okay, now, since you started with the 6 and the minus, we're assuming you're taking the derivative of the second part there. So this is just going to be a t times 1 minus t to the first power, right? Okay. But then if you take the derivative of this part and leave that one alone, that would be plus 3b1. You see that? Derivative of t was just 1 times t minus, or 1 minus t squared. Okay? That's the product rule. Remember that? Okay. You could just pull out the 3b and then just do the product of those two. And the first one is t times the derivative of that, which would be your minus 2 times t minus 1. Okay? 1 minus 6, I said it backwards. And then the second part of the product rule, remember you had the 3b1 on the outside, derivative of the first, 1 times the second. Okay? So you got that? Violet, I did it right. Okay. Y'all are gullible. I mean, y'all are believing. Okay, never mind. All right, how about the third term? What's going to happen here? You tell me how to start. Minus, you're going to start with a minus, so I think I know where she's heading here. That's to the first power, so that's just going to be a 3b2 t squared, right? That thing to the 0th power, we don't have to do that, so that's the first times derivative of the second. Now do the second times derivative of the first. That will then be a plus 6b2 t times 1 minus t, right? And then finally the last term, thank you very much. What's that one? 3b3 t squared. Who came up with this? Okay. Now, that's your y prime. Let's do the x prime. We're going to need that for your denominator. So, say again? I can't hear you. Can't we do what? I can't hear. Just change the b from y prime to yes, to an a. Yeah. We'll do that. But I thought you were going to say, can't we simplify? I was going to say, let's see if we can. Right now, I'm not seeing it too well. No. There's always something different in the terms. These are all three distinctly different. I mean, umpteens. Okay, so yeah, your x prime of t is exactly the same, you're right, minus 3a0 times 1 minus t squared minus 6a1 t times 1 minus t plus 3b1, the a1, I did it again, goodness gracious. Okay. All right. This is a1 here, and this is 3a1 there. 1 minus t squared minus 3a2 t squared plus 6a2 t times t minus 1 plus 3a3 t squared. What's that again? Okay, yeah, that's absolutely true. You could 3 out of everything will certainly make things simpler. So there, that goes. This becomes a minus 2. That goes. That goes. That becomes a plus 2, and that goes. And that also goes here. A 1 here, a 2 there, a 1 there, a 1 there, a 2 here, and a 1 there. You didn't know it was going to be this sloppy, did you? Okay. And that does give you pretty close to what they have here. Wait a minute. How did they get coefficients of... Oh, right. Got it. I thought there were some common terms. Nope, still not. How did they get coefficients of 3 rather than 2? We're dividing out 3's, and they've got 3, not 2. Oh, and they also have, I have a minus, they have pluses. Okay. Is there some... Oh, wait, I'm looking at the wrong place. Sorry. I was looking up at the top. The primes down here, I think we got it right. They left the 3's in there. Well, no, they didn't. They started simplifying a different way. Okay? I think ours is just as good, but let's see if we can rectify this a little bit. Okay? All right. Obviously, they do some combinings. This term, let's go back to it. This term is in place just as is. Okay, we're fine there. And the last term's in place just fine. Okay? It's the middle terms they do some combining on. So here's what we're going to do for those. It's the ones with the A1s and the B1s. Okay? So far, that term and that term are fine. Okay. So let's combine those. All right, let's go back to the 6's again. Minus 6 B1, and notice that's going to be t minus t squared, right? I said B1 and broke T1. I don't know where that came from. That's minus 6 B1 times t minus t squared. Okay, if you combine these two. Okay, well, not quite. Not quite. let's continue. That's just the first one. Plus 3b1, and what they have here is a 1 minus 2t plus t squared. Do you buy that? I'm just expanding. This is that term, and this, I'll put the 3 back in. This, I've expanded this, right? Okay. Now what they're doing is factoring out the 3, just for those two terms, and the B1, and I guess we'll do the minus with it. And what that gives you is a 2 here and a 2 there. Okay? Did they? No, they did a plus, sorry. Okay. So let me go back. Trying to reproduce what they did. Okay. When you, yeah. Plus 3b1, and this would leave you a minus 2t minus 2t squared. Okay, factor out that, and then you have a plus 1 minus 2t plus t squared. Okay. And if I'm combining like terms right, that's going to be a plus 3b1 times 1, there's the 1, minus 4t minus t squared. Is that what they got? 1 minus 4t minus 3t squared. How did I get that? Just that one. They got a plus. Oh, wait. Yeah, sorry. Let's think on this again. If you factor out a 3b1, that leaves a minus here, but that's a plus. That's the plus. I'm sorry. I missed that one. So that would be a plus 3t squared. Minus 4t plus 3t squared. Got it. Okay. Let's do the same thing with this one. Again, we're going to leave the 3's and the 6's in there for now. That would be a minus 3b2 t squared plus 6b2 t minus t squared. Okay. I combine those. And I think, do they leave the sign in there? They leave it a plus. Trying to do what they did, and it's not particularly easy. So let's do a plus b2 like they did. And this gives me a minus 3t squared. And this will be a minus 6t squared. Sure looks like that to me. That would be minus 9t squared, and that's not what they get. And then they would have a plus 6t, and that's not what they get either. They get a multiple of that. I think they left off a 3. Sorry. Do y'all see that? It seems like to me this has to be a 3 here and in the book. They don't have it on the slide, I don't think. Let me just scroll up and see. No, they don't. But in the book, I know it's such a mess, it's hard to see. Here's what they got. I'll do the x prime since it's right there. X prime of t. And they got the minus 3 a0 1 minus t squared. We know that's true. Okay? Then they do a plus 3a1 times 1 minus 4t plus 3t squared, which is, I got that too. But then they have a plus a2 times 2t minus 3t squared. I've got that they need a 3 there. But we'll check that in just a second. And then we know the last part is indeed plus 3a3 t squared. So I'm with you. I think we could have factored out a 3 everywhere. They don't have a 3 in front of that a2. And I think our work was right. Okay? So let's go back and check it. The terms with a2 in it were these two terms, and that was a minus 3a2 t squared plus 6a2 t squared minus t. Okay, let me go back and make sure we didn't write something because we only did that once. So let's see. The A2 term was 3a2 minus 3a2 t squared. Yeah, that's what we got. Then the second one was plus 6a2t times 1 minus t. Plus 6 a2t times yeah. Now, there's one place I made a mistake, and that might be it. I put t minus 1, it's supposed to be 1 minus t, isn't it? But I don't think. Okay. Okay. But I don't think I made that error anyway. I think it's 6a2, and it's not t squared minus t, it's t minus t squared. Yuck. It's not taking my eraser. There we go. Okay. T minus t squared. Believe that's right. Okay. Now, if you factor out, okay, let's expand that. That's a minus 3a2t squared plus 6a2t minus 6a2t squared. Okay. Looks like a minus 9. A2t squared plus 6 a2t, and if you factor 3 out of that, that'd be a minus 3a2 times 3t squared minus 2t. That's what I get. And they get an a2 times 2t minus 3. I mean, I wrote them in different order. I think there's a 3 in there. I think you're absolutely right. 3 factors out. I don't know what happened to theirs. I can't see it. Seems like to me there's got to be a 3 here. Okay, because we got it. So you could, again, factor all the 3's out. And I think that leaves us with, and we'll divide them out too, a minus a0 times 1 minus t squared plus a1 times 1 minus 4t plus 3t squared plus a2 times 2t minus 3t squared plus a3t squared. Okay. See, in the next line, they divide them all out anyway. I think they just left off the 3's in front of the a2's and the b2's. I can't see any other way. Now, if you evaluate that at t equals 0, then yuck, and do your prime there. That's what we're interested in, is dy dx at t equals 0. Okay? And that's going to be y prime over x prime. So let's go back to taking those out, and we'll get, man, it's so confusing now. At t equals 0, that term goes away. These two terms go away. These two goes away. That goes away. So all we're left with no, I'm sorry. The first one didn't go away. At t equals 0, this one didn't go away. Sorry. I was trying to get too much out of the way first. This term stays 1. That term goes away, and the rest of them do. Okay. So that's a minus a0. Oh, okay. This is a b0 plus b1 over minus a0 plus a1. Okay. And that's exactly what they get. Except they reverse the signs, which are fine. And what do we have? This is exactly that. Okay. Sorry about that. I spent all that time trying to figure out what happened to the 3 here, and they just left it off. Sorry about that. I thought they had it right. And then your books, are they missing the 3 on that? Yeah. And there's no way around it. The 3's have to be there. Sorry I took that long to find out their errors. So I just wrote them in, but I'm going to write them in more boldly. Okay, so next time I won't make that error. And you get the same thing for your slope. The slope of that one and the slope of this one was the same. Now, what we didn't do was show that the slope at P3 are the same. I'm willing not to do that one, because that was not going to be quite as easy to do. Because it's not going to be a lot different, but it is going to be a little bit different. So anyway, I think that's all we do with them, and so frankly, it seemed like much ado about not much. So let's move on to area under a parametric curve. And by the way, the old slide set included this. The new one, the new book doesn't have it. Do you have this figure in yours? You don't? Okay. Somewhere, well, okay. And this is a hand sketch made in 1964 by Pierre Bézier, which I find that interesting. Oh, no, that's right. Okay. I was thinking they had him dying in the 60s, but he invented it in the 60s. Okay. Made that by Pierre Bézier for the French auto manufacturer Renault. And basically, you can almost see his curves in there. I mean, the Bézier curves fitting things together there. Okay. So that wasn't in your book? Okay. I don't know why they threw it in here. It wasn't in my book either. Okay, but I thought maybe in the older edition it was. And they end it there. Not fair. Where is area under a parametric curve? Thank you very much for making me have to do all this writing. Okay, so what I'm going to do is clear this. Do you have this section area under a parametric curve at the base after the example 10? Is your example 10 what we just did, the Bézier curve? Was that your example 10? Yeah. Okay. Do you have anything after that? Summary. Okay, the new text, the new edition, has this, area under a parametric curve. Okay, so this isn't Bézier curve anymore, so forget about that figure there, but I'm just going to use the slide. As we know, the area under a curve given by y is equal to h of x, okay, when h of x is positive, okay, greater than or equal to 0, for all a's less than or equal to x, less than or equal to b, okay, is given by area under a curve would be the integral from a to b, h of x dx. Nothing new there, is it? Area under a curve, as long as that curve is never negative, it's just divide the h of x into your little rectangles, width dx, and the height times the width, that's going to be the area under the curve. Okay? This is A, area under the curve. Now, when the curve h of x is traced once by a parametric curve, c of t, okay, and that c of t is your ordered pairs, x of t, y of t, parametric curve. That is your c of t, as in figure 14, which you don't have. So I'll sort of draw you, basically, it's just a generic curve. This is the x-axis, here's the y-axis. This is your x at t0 and your x at t1. Here's your curve up here, c of t, with those coordinates. And your y, by the way, is y of t0, y of t1 type thing. If this is your curve, the area under that curve is given by that equation. Okay, we know that. Okay. So your h of t0 we're calling A, h of t1 we're calling B. Okay? X of t0, I don't know what I said. Okay. Then we can substitute, replacing the y is equal to h of x by y of t and dt by x prime of t dt, yielding the formula, this one. Now, notice here, here's what they're saying. Y is equal to h. We already know y is equal to h of x, okay? So that's the y value, okay? So now our integral, this integral here, will become the integral of your h of x is your y. Y is a function of t, okay? Now, the part that's a little different here is your dx, okay? And here's what you have to do, okay? Dx dt okay. This seems bizarre, but it's really what they're doing here. Times dt is equal to dx. Now, I know that looks a little bizarre, doesn't it? Okay? That dx is equal to dx dt dt. Okay? But at least it looks like that kind of makes sense. What is dx dt? This is your x prime of t. Okay? So your h of x was the same as your y. And the y is a function of t. And then your dx that we had here, that is x prime of t times dt. Okay? And that's what they came up with in their figure 11. Okay? Now, but now not going from a to b, your new variable is t, so it's going from t0 to t1. Your a here was x at t0, your b was x at t1. So now since you're integrating with respect to that. So that's the transformation they make. All right? That's now your parametric equation. So let's look if we can to example 11. I know your book doesn't have it, but the others do. And let me clear this, but keep that in mind. In fact, what I think I'll do is erase everything else, okay? Hopefully I won't need it. Watch me need it, but I'll try my best to get by without it. But I do want to leave the conclusion that we had there. Okay. All right. Example 11. Find the area inside the ellipse of example 5. Example 5 was back on page, it looks like, actually it looks like to me that's example 6. No, here it is. It is example 5 of this ellipse. Okay, I'm going to write it down the way they did. X over a squared plus y over b squared is equal to 1. Okay? And they tell you that's parameterized by c of t is equal to a cosine t, comma, b sine t. And by the way, then, and this is good for minus pi less than or equal to t less than pi. Okay, they didn't do it equal sign on that place. Now, let's see how much else they want from there. Yeah, no? In example 5, they say plot that for a equal 4, b equal 2. In this example, I don't think they're using, are they? No, they're leaving the AB alone. They're not substituting values. Okay? So, with that in mind, let's see if we can do the integration like we just did. Therefore, the a is equal to the integral. Okay? Now, they're doing a little trick to you here too. Probably, I can't believe I didn't do this. I almost always draw pictures, but since it was in the book, I didn't. But let me draw this for you. Okay? Here is the ellipse. It really doesn't matter which way I do it, but let's just do it something like that. Okay? And we're wanting the area of the ellipse of example 5. Okay? Now, what they say to do is go from minus pi halves to pi. No, minus pi to pi. Starting here, going around here, and coming back there. Okay? That's what they're doing, one time around the ellipse, all the way around the ellipse. Okay, the first thing they say is, notice that if you just do the top half of that and double it, you'll have the area of the ellipse. Okay, so that's the first thing they're going to do, is only go 0 to pi. Okay, not minus pi to pi, they're going to just double it. Okay, that's the first thing. And those are your t values now. Just like here, except you're only doing 0 to pi, but doubling it. Okay, your y of t is b times the sine of t. Now, we also need to find what x prime is. X of t is equal to a cosine t, so we need to know what x prime of t is. Any guesses? Say again? Okay. Okay. A little louder. I heard sine, huh? A times the sine of t, one little minus, a negative a times the sine of t dt, basically. Yeah, we got our dt in there anyway. So then this will be times a minus a times the sine of t. Then you got your dt. Well, the a and b's are constants, so let's pull out a minus 2ab, the integral from 0 to pi of, I pulled out the minus sign, sine squared t, dt. Now, I don't know if you remember back when we did integrals of trig functions, we did sine squared. If you don't remember that, right off the top of your head, you can go to the back of the book and see what the integral of sine squared is, and that would be 1/2 u, ours are t, so this part right here is going to be 1/2 t minus 1/4 sine of 2t. Now there's another way to express that too, and we're going to evaluate that from 0 to pi. Right? Now we got the minus 2at ab out front, but we're just doing this part. Okay? I can see the first part is going to be pi over 2, right? Plug in pi for t, and that'll give you pi over 2. The 0 won't give you anything on that. Okay, minus 1/4. What's the sign of 2 pi? 0. And what's the sign of 0? 0. Okay, so that's not going to give you anything. You just wind up with the pi halves here. So what we have now is the area is equal to, the 2's will go out, and you're just left with AB. Okay, with a problem that it has a minus sign. Oh, I'm sorry, pi AB. With the problem of the minus sign. Okay, and I haven't quite worked that one out yet. Oh, wait a minute. No? Okay, B sine theta. Okay. What's that?
What happened to the minus?
That's what I'm trying to figure out. They leave it off. That's the only thing I can figure out. If you follow their thing, you don't have it in your book. It says 2 times. Oh. They do. And I can't figure out quite why. The top half of the ellipse corresponds to 0 less than t is equal less than pi. You got that. And since that curve yields the graph of a function that is non-negative, we can find the area under the curve using the formula 10. Notice, however, that T0 is pi and T1 is 0. That's what happened to it. Now, where did that come from? Oh, I see. I think. Seems like to me they're doing here to here. Okay? But maybe they're not. I don't know. That's what happened to it. They say this integral is from pi to 0. There we go. And I haven't quite figured out why they say that yet. There may be a very good reason. And then when you flip those, you lose the minus sign. Okay. Now why they do it pi to 0 rather than 0 to pi, I'm not sure. Unless, oh, this is probably it. They're probably going from here to there. So this is your T0, that's your T. Yeah, that's probably it. I mean, T1. This is T0, that's T1. You're going that way, so you're integrating from pi to 0. Because the formula we have here is T0 to T1. Our T0 for this, integrating under this curve, would be from here to there. So that must be it. Okay. Strange, but probably true. And that way you lose the minus sign then. Okay. So we got the right answer, pi AB. All right, we want to look at preliminary questions here. Describe the shape. Let me go on and clear this. Okay. Describe the shape of the curve x equals 3 cosine t, y is equal to 3 cosine t. 3 sine t. Describe the shape of that curve. Anyone want to hazard a guess? It can be a wild guess. Anyone want to guess what that might be? Not an ellipse, close, but not quite. Ellipse would be if that 3 was not a 3 in one of those cases. Like one was a 3, one was a 4, that would be an ellipse. What if those 3s are 3s in both cases, though? Circle of radius 3. That's exactly what that is. A circle of radius 3. Let's make sure the back of the book agrees. A circle of radius 3 centered at the origin. I didn't say that, but I said it. All right. Number 2. How does x equal 4 plus 3 cosine t, y is equal to 5 plus 3 sine t, say this again. I can't hear you. Yes, exactly. You're right. I'm writing it down because I don't know if everybody has the same book, edition of the book. Differ from the curve in the previous question. Okay? And what were you saying? Okay. Yeah. Generally we call it translated or shifted or something like that. But yeah, I get your drift. To where? The first one I didn't say the center was at 0, 0. Now the center's at 4 or 5. Exactly. But that same circle of radius 3 is now shifted from the origin up to 4, 5. You're absolutely right. Okay? Let's see if they got it right. The center is at 4, 5. Yeah, not at 0, 0. All right? Number 3. What is the maximum height of a particle whose path has parametric equations x equal t to the 9th, y is equal to 4 minus t squared. What we're asking for is what's the maximum height of a particle whose path has those parametric equations. What would be your approach to that? Again, wild guess. Huh? Maximum height. What's that? Okay, we could take a derivative of what? Both, okay. Tell me what that would give you. dx dt is equal to what? 9t to the 8th. And dy dt is equal to t minus 2t. Now, what does that tell you? Okay, we'll do that. So dy dx is equal to dy dt on the top and dx dt on the bottom. And that would be, what's that? One more time. Yes, let dy dt equal 0. And what does that tell us? Okay, maximum or minimum, where will it be? When t is equal to 0. So it's going to happen when t is equal to 0. T is equal to 0, okay? And what is your y value when t is equal to 0? Four. Okay, that's your maximum height of 4. If you think about this, let's go back. Y is that. That's a parabola going like this. Maximum it can ever be is 4. Anything beyond t on either side is going to be dropping down from there. Plus or minus, doesn't matter. So that's going to be y is equal to 4. That is your maximum height. Now that's why I think it's asking for maximum height of 4. Yeah. And you probably did it the way they wanted you to do it. When you just think about it, it's got to be. Okay, so you can think about it too. Okay, that was number 3. Let's do clean slate for 4. Any questions before I get rid of these? Okay. All right. Yeah, that's right. Okay. Losing my mind here. Number 4. Can the parametric curve t sine t be represented as a graph of y is equal to f of x? Okay? Yay or nay? What would it be? Second, by is equal to f of sine of x, right? That x equal t and y is equal to sine t, then you have y is equal to sine x, right? Yeah, okay. How about this one? This curve, sine t. Can you express that as y is equal to f of x? What you think? The closest I could come, I think, would be this is saying x is equal to sine t, right? And y is equal to t. And the best I could come up with is say t equal inverse sine of x, right? And then y is equal to inverse sine of x. Now, would that represent everywhere? No. You're only limited there where it can be. But they didn't say everywhere. That may be what they imply. Let's see what they say. Yes, no. Okay. So not everywhere. Okay. That would come as close as what I could imagine you could, but that's still not going to represent it everywhere. Okay. This would be good at any values.
From where to where would it represent?
What's that?
From where to where would it be represented?
Minus pi halves to pi halves, because that's where sine, that's where inverse sine is defined for. Minus pi halves to pi halves, because you see your sine function does like this. You have to be 1 to 1, so it would be like this. Okay, and then your t would be limited from -1 to +1. So it wouldn't be everywhere. In a very small selected domain, you could make that happen, but not everywhere. And so the answer, I think, would have to. They said the answer is no, and I agree with them. Let's look at number 5, the A part. Describe the path of an ant that is crawling along up the plane according to, here's the ant's path or curve, C1 of t is equal to, it's a clever ant, f of t, it walks along in abstract functions, f of t. Okay? Where f of t is an increasing function. Okay? So describe the path of an ant that is crawling along a plane according to C of t is equal to f of t, where f of t is an increasing function. What's that? Yes, I think it would be going along a diagonal, but speeding up as you went, I think, because f of t is increasing, okay? Though I'm not absolutely sure about that. Not yet. It'll just be along a diagonal. Now, you don't know that it starts at origin. It could start anywhere, but it's going to be the diagonal. It could start up here and go up, or it could start down here and go up. The increasing function is always going to be going in that direction. That's my interpretation. Let's see what the book gives. The line y is equal to x traversed from left to right. Okay? So wherever you started, wherever you ended. We don't know where the t's began or ended, but anyway, we'll do that. Now the B part, compare that path to a path of a second ant crawling according to this curve. Here's its ant number 2, and this is f of 2t, f of 2t. Okay? And we're assuming it's the same f, an increasing function. So what would be your guess here? How would ant 2 compare to ant 1? I don't think it's backwards. I just think it's twice as fast. Okay. Huh? Oh, faster. I thought you said backwards. Okay. I think it would be twice as fast because at time t, the first ant, say, went f of t, f of t, f of tx, f of ty. The second one went to f of 2t, f of 2t. So it would be twice as far along in the same time period. So I think it would be the same path, the same diagonal, but going twice as fast. Okay, B is the same path traversed left to right, twice as fast. Absolutely. Okay. Number 6. Find 3 different parameterization. Let me go on and go to a clean slide here. 3 different parameterizations of the graph of y is equal to x cubed. 3 different parameterizations of that. Give me one. X equal t, y equal t cubed. Wouldn't that be it? Okay. That'd be y is equal to x cubed. And that would be for all t's. Okay. Now, I'll come up with one and you tell me if it works or not. Would this be one? X equal t squared, y is equal to t to the 6. Would that work? No. Why not? Those would only be positive values for x and y. This allows negatives for x and y. So you see, I think, therefore I am, I think you'd have to keep these odd numbers. So, 3, 9, and x equal t5, y equal t, what, 15? Yeah, I think those would work, okay? But I don't think the evens will. You see why? Because you couldn't cover all the values. Now, let's see what they say. C1 would be t cubed. C2 would be, they chose t to the cube root, t, that works fine. And t3 could be t cubed, t9, just like we did. So their other one was t to the 1/3 t. And that works fine too. Okay? Because you can take cube root of negative numbers and they'll be negative. Yeah, that would be fine too. You couldn't do the evens though, because that would give you all the values. One more. Okay, I think I'm going to have to start with a clean page here too. Match the derivatives with the verbal descriptions. Okay, how about I read the verbals and you give me which one you think it would be. The slope of the tangent line to the curve. Which one? C. I like that one. Vertical rate of change with respect to time. Yes, B. And horizontal rate of change with respect to time. dx dt. I think you're right there. Let's say that should be CBA. They don't have it in the back, so yes, but we're right. I don't know why they don't have it in the back. Did you have that 7th one in your book?
Yeah, I have that problem, but I didn't have the 2 problems that you just talked about.
Oh, really? Okay, wow. Okay, anyway, homework exercises here. Do any of the odds 1 through 5. Do any of the odds 7 through 13. Do either 15 or 17, or both if you choose. Do any of the odds, or I'll say either 19 or 21, or both if you choose. Do any of the odds 23 to 37. And either 39 or 41, or both. I'll let you choose. Any of the odds 43 through 47. Any of the odds 49 to 53. Any of the either 55 or 57, or both if you choose. And then any of the odds 59 through 65. And either 67 or 69. You choose. And then any of the odds 71, wow, through 83, and then either 85 or 87, or both if you like, and then any of the odds 89 to 97. Not many, but do a few. Right. All right, now, while we're there, I did see the folium of Descartes, so certainly Descartes would be a decent paper topic, but you could also say, what is this folium? How did he discover it? What use is it? You know, what applications would it have? You could pick several paper topics out of that. And then on the further insights and challenges, the only thing I see there that might be of interest, I'm not sure it would be the Traxx, whatever that is. I don't probably not pronounce it right. Traxx, okay. I don't know. You may find it interesting. You may not find it, or you may find it terribly dull. Okay, we're going to do next time 11.2. We're going to start in 11.2. 11.2 is maybe a little shorter section. Hopefully we can get through it a little faster. I will try to have your test ready for you next time. Can't promise. I've got one test I still haven't got made out that I need to finish making out. I've got it mostly made out. I've just got to clean it up some. And then I've got 2 or 3 deadlines coming up Friday, so I don't know if I'll have time to get it done or not, but I'm going to try to. Maybe this afternoon, but if not, soon. Good deal. Any questions? And I'm afraid we're out of time, so we will pick up